Hello, welcome to this session of Prolink Accountancy and Management Consult, where we continue our detailed look at the CPA syllabus and indeed our detailed look at probability. My name is Norman, your tutor for quantitative techniques. So today we shall look at one of the most fundamental topics in the syllabus, which is Bayes' theorem, as we continue our look at conditional probability. Bayes' theorem looks at the possibility of an event occurring with prior knowledge. So it is quite important that when we are using the theorem, already we shall be having some prior knowledge of an event, and then we shall be asked for to sort of establish a cyclic relationship of events that have occurred. So the theorem was invented by the 18th century British mathematician Thomas Bayes, who also happened to be a reverend and made some extensive discoveries in the field of statistics and applied mathematics. You'll hear of many fields of statistics, but to which he made contribution, particularly in Bayesian statistics. But what is important for us is that the theorem allows us to update the predicted possibilities of an event by using new information. Already we have some background information, and as I said, we are trying to establish sort of a cyclic relationship. So that's quite important for us and for what we are going to be doing. So this theorem is extensively used in the field of finance and applied mathematics, particularly in the area of risk evaluation, which makes extensive use of Bayes' theorem. So Bayes' theorem can simply be denoted if you have two events: probability of A given B, which of course is probability of A intersection B, over probability of B. So Bayes' theorem itself is probability of A given B shall be equal to probability of B given A times probability of A over probability of B. So we have two events which we have the opportunity to define. Events A, we have events A and events B. So we're establishing a relationship. If we know the probability of event B occurring, given that event A has occurred, what is the probability of event A occurring given that event B has occurred? So as I said, it's sort of a cyclic relationship, and it will be quite interesting for us to know how to establish these probabilities. We have to know not to confuse what is the prior event. Do not mix the prior events. A lot of students do mix this up, and as a result, many students are unable to figure out correctly which is the prior event and which is the preceding event. So we shall look at that and try to give ourselves some clarification on that, which will be important for us in this session, as is in the exam. So we have the opportunity to define those events. Of course, probability P of A is the probability of event A occurring. Probability of B is the probability of event B occurring. Probability of A given B is probability of event A occurring given that B has occurred. And B given A is that of event B occurring given event A has occurred. And probability of A intersection B is the probability that both events have occurred, or both events occurring. So that is our basic Bayes theorem. So we also look at a basic derivation for Bayes theorem, which again makes use of the relationship of conditional probability, and we are able to establish that sort of cyclic relationship. So if we have two events, once again, A given B, whose probability, of course, from conditional probability, we know is probability of A intersection B over probability of B. That can be our equation 1. So if we have probability of A given B, what is the probability of B given A, just using the conditional probability. So we can also establish that relationship. So probability of B given A is also probability of A intersection B over probability of A, because this is the probability of B given that event A has occurred. So we divide that by probability of A. And if that is true, then we can make A intersection be the subject from this equation of B given A. And so probability of A intersection B is equal to probability of B given A times probability of A. So we have two equations, and we can substitute equation 2 in equation 1. So if we substitute equation 2 in equation 1, we're able to come up with the basic Bayes theorem, which denoting events A given B is probability of B given A times probability of A over probability of B. Now the detailed derivation may be a bit complicated, but also uncalled for. But this is our basic derivation, not so important in itself, but again, it is to establish our understanding of the theorem. Nobody is going to ask you in quantitative techniques to derive Bayes theorem, but we are able to cement our understanding of conditional probability in the most simplified way. So if that is true, then we are now saying for any number of events, the probability of A given B can then be denoted as probability of B given A times probability of A over probability of it's supposed to be over probability of B, but probability of B can be through a number of events. That's why we are saying probability of B given A1 times probability of A1 plus probability of B given A2 times probability of A2, and so on, up to AN, the nth event in itself. So that is a bit tapping into the knowledge of total probability theorem. But again, it's not as complicated as it can be. So the most important thing is for us to know that using Bayes theorem, we can look at a number of events, and extensively. If we have a number of events, then we can extend this relationship of Bayes theorem to an infinite number of events. And there you have your equation. Not so much effort that you need to memorize it, but rather to understand what is important is the denominator, which is probability of B. And using total probability theorem, probability of B can be established in a number of regarding the number of events. So if you have n events, then you'll have to multiply that by n times. So that's quite important for us. So we then look at a special case of Bayes theorem. If we talk not so special in itself, but we shall just denote that as a special case. Why are we saying this? We are looking at complementary events instead of looking at 100 events. Supposing you have a set that is exhaustive, that you have events A and events B. Maybe you're looking at a sample, you're looking at a student population. A student is either male or female. So a student is either male or not male. So you can look at these two events as complementary events, and that's a special case of Bayes theorem, which instead of looking at infinite events, only looks at two events. So using our equation, we can extend the probability of A given B shall now be probability of B given A, of course, times probability of A, times probability of B given A, times probability of A. But this time we have, instead of having the second event, it's now B given A complement times probability of A complement. So we note that probability of A and probability of A complement are an exhaustive set. So probability of A and probability of A complement is equal to 1. So that is quite the special case that we are talking of. As I said, nothing so special about it, but it simplifies the Bayes theorem. It simplifies the Bayes theorem for us. and we are able to look at exhaustive events using Bayes' theorem. So, having looked at a very important overview of Bayes' theorem, we can now look at some examples, what would be typical exam scenarios, to be able to see if we can solve the problem using our applied knowledge. So here is the first example. Here is the first example that we are going to look at. So the question says, at a university, 4% of men are over 6 feet tall and 1% of women are over 6 feet tall. So this looks to me like a scenario in which we would use the special case of Bayes' theorem. We have a sample set of men. We have a sample set of university students who can either be men or women. So 4% of men are over 6 feet tall. If they say 4% of men are over 6 feet tall, what are we looking at? So we have two events. We either have a man or a woman. So they are still telling us the total student population is divided in the ratio of 3 to 2. So we have already percentages, probability that a student is male, or probability that a student is female. So the 3 to 2 is in the favor of women. So probability, we shall come back and look at the interpretation of the probabilities. So the probability that a student is female should be 3 over 5, because they are saying the ratio, the total ratio 3 plus 2, they are being 5. And so the ratio being in favor of the females, so probability of female is 3 over 5. In a similar understanding, the probability of male is 2 over 5. Now if that is true, and what do the other probabilities mean? 4% of men are over 6 feet tall. So this again calls for us to interpret which one is the conditionality. If they say 4% of men are over 6 feet tall, this would imply that probability of somebody being tall, given that is a man. So in this instance, somebody is a man, but is also tall. So what is the conditionality? He is tall given that he's a man. So that is how you can express it. So probability of T given M is 0.04. And they're also telling us probability that a woman is tall. So this will imply that probability that is tall given that he's a woman or female. And that will be your 1% or 0.01, whatever favors you. You can decide to use decimals or fractions. We continue looking at the question. If a student is selected at random from among all those over 6 feet tall, what is the probability that the student is a woman? So this time now, they are no longer asking us the probability that is a woman, or the probability that is tall given that is a woman. But there is no argument about this. The student is already tall. What is the probability that a student is a woman? So we are given the probability that a student is tall given that she's a woman, which is 1%. And now they are asking us, what is the probability that the student is a woman given that she is tall? So that is Bayes' theorem, which we can look at. So we can arrive at the solution. So again, what is very important for us is to define the events. You can use any letters, but in this case, I would suggest that you use letters that, apart from the conventional A given B, we can denote letters that can give us an understanding about what we are doing so that we don't confuse ourselves. So in this scenario, we are saying let M be the probability that a student is male. So if M is the probability that a student is male, so F will be the probability that a student is female. And remember that these two events exhaust the sample space. And let T be the probability that a student is over 6 feet tall. So we shall use T. So if that is true, we know that probability of M is 2 over 5 and probability of F is 3 over 5. So probability of T given M is 0.04 or 4% or 4 over 100 in itself, and probability of that the student is tall given that he's female is the 1%, which is 1 over 100. So if that is true, what we need to find now is probability that the student is female given that they are tall. So that is F given T, which we are going to look at. So using Bayes' theorem, of course, using the special case, probability of A given B is denoted as on the screen. And if that is true, we can extend our relationship to what we want. We want the probability of F given T. So using Bayes' theorem, just connecting A and B and F and T, probability of F given T is now probability of T given F times probability of F over that probability of T, and probability of T is probability of T given F times probability of F plus probability of T given M times probability of M. We can begin to put in values in those. T, probability of the student being tall given that she's female is 1 over 100. The probability of the female is 3 over 5. And probability, so we put that in the denominator as well. Then probability of the student being tall given that they are male is 4 over 100. And probability of male is 2 over 5. And by my calculator is 3 over 11, which you can also make the confirmation of. So you can see it is not as complicated as it looks. What is important, which we need to understand, or what could be a confusion point for many students, is denoting the conditional probability, denoting that conditional probability. So if let's go back to the previous screen. So do not confuse this with if they tell you 4% of men are over 6 feet tall. So this is the probability that somebody is tall given that they are a man. So they are already a man. So that is probability of T given that the student is male. Do not confuse yourself in any way. The first thing is the student being a male. So it is on condition that he is a male. So first is a male, then the student is tall. So that is a very important defining point, and where most students go astray, almost fail to even begin the question, because they cannot make such a basic interpretation. If they say 1% of women are over 6 feet tall, the student, somebody is first a woman, then she is over 6 feet tall. So this is the probability that the student is tall given that she's a woman, not probability that she's a woman given that she's a tall. No, given that she's tall. She is first a woman, then she is tall. So this probability that she's tall given that she's a woman. So that's quite important for us there. So we can look at the next example. Can look at our example 2, which is also a typical exam scenario. This is got in the field of manufacturing. Factory production line, we can read through together as we make the interpretation of some of the basic interpretations in the question. A factory production line is manufacturing bolts using 3 machines, A, B, and C. Of course, if it's using machines A, B, and C, we know that it's either manufactured by machine A, or machine B, or machine C. And as such, the probability of machine A, B, and C have to be exhaustive. They have to total to 1 or to 100%. We continue. Of the total output, machine A is responsible for 25%, machine B for 35%, and machine C for the rest. So the rest is the difference between the total of 100 minus the total of 25 and 35. We continue. It is known from previous experience with the machines that 5% of the output from machine A is defective. So we are being told 5% of the output from machine A is defective. So if 5% of the output from machine A is defective, this is the probability that it is defective given that it is from machine A. Likewise, 4% from machine B is defective and 2% from machine C is defective. This is the defining point of Bayes' theorem, which determines whether you go astray or it turns out to you to be a very easy question where you can save time with a few lines of calculation. If you cannot interpret this line, then you're done, because everybody can know that probability of A is 0.25, probability of B is 0.35, and probability of C is the difference, which in this case I think is 40%. That's not a big deal. Where students go astray is determining these conditional probabilities, and they get lost among themselves. So here is the question. A bolt is chosen at random from the production line and found to be defective. What is the probability that it came from the first scenario, machine A, second, machine B, and the third, machine C? Let's go straight at the solution. We have already had some basic interpretation. Here. So we shall begin by defining the events as usual. So let D be the probability that the bolt is defective, and let A be the probability that bolt A is from machine B. In a similar tone, B will be the probability that the bolt is from machine B, and C is the probability that the bolt is from machine C. As I told you, A, B, and C are exhaustive events. They exhaust our sample space. So if probability of A is 0.25 and probability of B is 0.35, which was 35%, probability of C is 40%, which is 0.4. So if probability of C is 0.4, we have exhaustive events. So we can continue. Probability of D given A is 5%, which is 0.05. This I told you is the defining point of the question, because after that is 2 or 3 lines of the calculation, and the answer will come from the calculator, not from the student. So it is nothing difficult there. But where we would be worried that students go astray is defining these events. Once you fail, you are done. The question will become so hard. So probability of D given A is 0.05. Probability of D given B is 4%, which is 0.04. And probability of D given C is 2%, which is 0.02. So that is also the probability of a defective bolt coming from the respective machines there. So if that is true, then we can state our statement of Bayes' theorem, this time for 3 events A, B, and C, which we already agreed are exhaustive events. So using our Bayes' theorem for part A, probability of A given D will be probability of D given A in the numerator times probability of A. And we have the denominator there exhausting the event, taking the total probabilities of the defective machines. This will apply for all the events, because first we are calculating probability of A given D, and then we shall calculate the probability of B given D. So the denominator for all of them, and even the third one, C given D, all of them are probability of D. So we have to exhaust the denominator there and take probability of D given A times probability of A, probability of D given B, multiplied by that of probability of B, and probability of D given C, multiplied by probability of C. So that is our statement for Bayes' theorem. And if that is true, we can put in the figures. Nothing of much work to do here. The figures are quite obvious, especially the fact that we have interpreted it already. The D given A is 5%, and probability of A is 0.25, and then we also have probability of D given A. That's probability of machine A making a defective bolt is 5%, and that of machine B is 4%, and that of machine C is 2%. But also the probability that the bolt came from machine A is 25%, 0.25. That of B is 35%. Sorry, here it's supposed to be 35%, and then that of machine C is 40%. So our answer is expected to be 0.362. I think it has no impact on the calculation. And then we go to the second part. Probability of D given probability of B given D is still the same here. The only difference is the denominator. So if that is true, inputting those values, we can input in those values, and that is supposed to be 0.406. Let's just go a bit up. Your probability of B is supposed to be 0.35, so you'll help me and make that correction. You'll help me and make that correction there. Then you'll confirm the final answer. You'll confirm the final answer there. So probability of B, this is supposed to be 0.35 for all the scenarios. So you'll pardon me there, make the correction and come with the correct computation. But what is important is how to understand these events. So we go to the third part, which should be straightforward, given the effort we have put in the first two parts. Probability of C given D is that of D given C times probability of C, and we input the denominator, and we can enter our values and come up with the answer. So that is a typical exam scenario of Bayes theorem. So as I told you, the defining point is when we look at our interpretation of these events. If we cannot do that, we cannot attempt the question. Here is the important line. It is known from previous experience with the machines that 5% of the output from machine A is defective. So this is defective given that it is from machine A, not from machine A given that it is defective. That's what we have to evaluate. And then the 4% is defective given that it is from machine B. So it's first from machine, the conditionality is it being from machine B, and the third part is it being from machine C. So that's quite important for us, and we are able to proceed with our question. And as you can see, it's a few lines of calculation, extremely simplified. The only effort is in interpreting the events. So that has been a look at Bayes theorem. So I can leave you with some questions to look at, which will be quite important in cementing our understanding. The first one, a typical exam scenario, which still looks at defective items. From a batch of 100 items, of which 20 are defective, exactly 2 items are chosen, one at a time without replacement. Calculate the probability that the first item chosen is defective. Then you can go on. That should rather open our understanding of conditional probability. The second one is not so far from the example which we have looked at, and then the third one also talks at machines, this time with even 2 events, so it should be much easier than the question which we this time with 2 machines should be much easier than the question which we looked at, which had 3 machines. But again, will help you to cement your understanding. If you can have a go at this, that would be very good. So feel free to do this question, and if you have any challenges, then you can contact me. So that has been our look at Bayes theorem. Feel free to subscribe to our YouTube channel, so that you can get the latest videos, and in case of any suggestions, you can also get to us in the email below this video. Otherwise, thank you so much. Thank you so much for your time.